It's not working. Okay. Can someone post on the chat that we're having technical difficulties? This worked yesterday. Oh, are we streaming?
Yeah, we're still waiting for Astronomy on Tap.
According to Micah, she can see us or hear us. There's like a communication error where the like actual stream isn't, so like the actual link, YouTube link isn't, there's like two different links, but they're not like communicating with one another. Does anyone want to, she can see us or hear us?
Yeah, if you just go to the stream on,
there's like a communication error where I see what happened. Okay. So we are live, apparently. I'm gonna do something real quick to switch the links. Okay, we can start now. Are you ready, Nico?
I am ready.
Okay. Well, that was a little difficult and we might have to look into the issue later, but we are live. Welcome to AoT, the Bryan College Station chapter. I am MC Blue Moon Skater Girl, and this is MC
MCNC, MC Nico Cleary.
NC. That's not confusing. How are you doing tonight, Nico?
I am doing wonderful. How are you?
I'm doing great, except for this technical difficulty that we had. You'd think that after a year and more of pandemic would be used to this, but apparently not. Let's get started. Okay. So this is AoT number 43. Remember to participate in our trivia. We're still doing trivia, and you can go to tx.ag/AOT trivia to find it. And this month we're doing a Hubble James Webb Space Telescope face-off. And the winners will be emailed, and you can get a free t-shirt or a free drink at the Grand Stafford next time.
And as always, it helps us out a lot. Remember to like and subscribe on our YouTube channel, Astronomy on Tap BCS.
Also, follow us on our social media pages. This is where we update people about our next events and also whether or not we're going to go virtual. And you can follow us on Twitter and Instagram at AOT_BCS, or you can go to Facebook and look up AOT BCS. And then we have events posted there. And also we have our main website, astronomyontap.org/events, and all of the Astronomy on Taps across the world and the US are posted there. So you can check out other Astronomy on Tap events.
And if you would like to go the extra step above and beyond, help us support our venue at the Grand Stafford Theater in Bryan. Venmo Jose-Quintana-20, and be sure to put Stafford tip in the description. And we also have online donations available, Venmo and Cash App at AoT BCS. If you donate $15, you can get a free AoT t-shirt or mug. We have brand new mugs. Thank you, Silvana, for the new mugs that just came in. And
these are our new mugs.
Get yourself a mug.
$15 donation as well. So our next Astronomy on Tap, until further notice, is going to be in person at the Grand Stafford Theater and on YouTube. We're also live streaming our Astronomy on Tap in-person events. So if you aren't a local, you can still check us out. And the next event is going to be February 23rd, 2022. And today, this is our first Astronomy on Tap of the year. How exciting.
And just remember, we are constantly monitoring the live chat. Post your questions. We will respond to all of them.
Okay, so let's get started with the trivia tonight. The Hubble James W. I keep saying James WST. JWST face-off. So unlike other virtual events that we've had, we used to not go through trivia, but today we're going through trivia. So we can all do it together. So everyone take a second, pull out your phone or on your laptop, go to tx.ag/AOT trivia. Are you ready, Nico?
Of course, I'm ready.
Do you know the answers to all the questions, do you think?
I could probably do pretty well. I would hope.
And yes, Nico is wearing the AoT BCS shirt. Woo!
$15.
Okay, you can start us off, Nico.
I still can't see your screen.
Oh, interesting. Technology is not working with me today. How about now? Can you see it now?
I cannot.
Okay.
There is. I see a question on the back. No, there's nothing on the back. It's just our lovely AoT logo on the front. It's great. For only $15, you can get a free AoT t-shirt.
Can you see it now?
There we go. Go ahead.
Oh, it is.
I see the announcement slides.
Yeah. Okay. Woo! Yes.
Yes, we're good.
Wow, it's just like I think it's Mercury's in retrograde. Just kidding. That was a joke to everyone. Haha. Okay. You can sort of softly go.
Right. Question number 1. How large are the primary mirrors of each of James Webb and Hubble? JWST 21 feet, HST 8 feet. Unfortunately, these are in feet, not in meters, like a sane person. B, JWST 15 feet, HST 21 feet. C, JWST 50 feet, HST 12 feet. Or D, JWST about 8 feet or HST about 4 feet.
Question 2. What wavelengths can the James Webb Telescope see? A, 100 nanometers to 2.5 microns. B, 0.3 millimeters to 3.6 millimeters. C, 0.6 microns to 28 microns. Or D, 55 microns to 672 microns.
All right, question number 3. About how large is the sun shield on JWST? A, about the size of a Ford F-150. B, about the size of an Olympic swimming pool. C, about the size of a football field. Or D, about half the size of a tennis court.
Dun, dun, dun. Question 4. Which telescope was launched into space by a space shuttle? A, Hubble. B, James Webb. C, neither. Or D, both.
Question number 5. JWST recently reached its final destination. How far away will it be for the remainder of its life? A, approximately 350 miles. B, 100,000 miles. C, 1,000,000 miles. Or D, 5 million miles.
Question 6. When was the original JWST launch date? A, 1996. B, 2007. C, 2018. Or D, 2021.
If you saw my in the news talk from December, you know the answer to that last question.
True.
Question 7. What is the name of the first telescope that orbited the L2 Lagrange point? A, Pioneer. B, Voyager. C, Herschel. Or D, there hasn't been one yet. James Webb will be the first.
Question 8. How many instruments are on board each of the telescopes? A, JWST 10, HST 2. B, JWST 4, HST 6. C, JWST 5, HST 3. Or D, JWST 8 and HST 4.
Question number 9. What was the original name of the James Webb Space Telescope when it was first proposed in 1996? A, the Very Large Space Telescope, VLST. B, the Far Orbit Infrared Space Telescope. C, the Near to Far Infrared Telescope. Or D, the Next Generation Space Telescope.
VLST, foist, no fit, or
NGST.
Sorry. Okay, question 10. Who is Hubble named after? Edmund Hubble, who led the team that detected the first black hole merger. Edwin Hubble, who discovered there are other galaxies other than the Milky Way. Edward Hubble, who pioneered a new technique for exoplanet detection. Or Elvis Hubble, a singer and fanatic astronomy fan who donated a large sum of money to the project. Go Elvis. I don't know. Okay, and that is our trivia. That was really fun. Did you have fun, Nico?
I had a blast. How many do you think you got right?
Like half, maybe more. What about you?
I don't think I would have gotten a perfect score, but I think I did pretty well. I think I maybe would have gotten like 8.
Okay. That's what we need to pass our astronomy exams. Okay, so our first speaker, Lauren Alderodi, is a 4th-year astronomy grad student. Fun fact, Lauren likes horses and to bake vegan food. Lauren is really good at making non-vegan stuff vegan. So, do you have any other fun facts, Nico, that you would like to ask or say about Lauren?
Lauren has the shiniest pair of Doc Martens that I've ever seen.
Thank you for that introduction.
Take it away.
All right, let's go. All right, we can all see my slides okay?
Yes.
Check. Okay,
Yeah,
great. Just checking because there were issues with that earlier. Wonderful. All right, welcome to my talk. I'm Lauren. My talk is called The End of the Universe as We Know It. I hope you're all feeling fine tonight. Don't throw tomatoes at your screen for that joke. Anyway, let's get existential. In order to talk about the fate of the universe, we need to talk about what's in the universe. Only about 5% of the universe is irregular matter. Irregular matter is stuff that we can see. So like you, me, stars, memes, opossums, and other cats are all regular matter. About 27% of it is dark matter, which is matter that's kind of been giving astronomers some trouble for a while because it doesn't interact with light. So we can't see it, but we know it's there because it has mass. One of the things that mass does is it affects how the universe is curved. So if something has a lot of mass, it creates a big warped location in space-time. Smaller objects with less mass create warped areas as well, but they're less warped. So if you imagine like a rectangular sheet of spandex that's pulled like tight and you dropped a balloon and a golf ball on it, the golf ball makes a bigger dent in the fabric than the balloon. That's what mass does to the universe. These warps are important because light travels along these paths. So light that does not go near anything massive travels in a straight line like we would expect, like the line on the left. And one that goes near a massive object curves around it in accordance with how the mass distorts space-time. So like this arrow on the right that's traveling straight and then dips into the hole and then comes out. Okay, great. Now we've talked about curvature. We're going to return to curvature. So put a pin in this, don't forget this. First, we need to talk about dark energy. Dark energy is the largest bit of the universe. It's about 68% of it, and it's the stuff that's making the universe expand. And not only is it expanding, but it's expanding at a constantly accelerating rate. Now, the way the universe expands matters quite a lot to, if we want to talk about the ultimate fate of the universe, it is important what it's doing now and what it's done in the past. This picture from left to right shows the cartoon timeline of our universe from the Big Bang until now. In the very beginning, there is this period of extremely rapid expansion called inflation. Now, what inflation did was it made stuff expand so fast that these tiny energy irregularities, sorry, there's a loud noise outside. Anyway, these quantum fluctuations, which are also pointed out on the picture, these are just little energy irregularities. And inflation expanded the universe so fast that they weren't able to smooth out and homogenize. So because of these quantum fluctuations, these energy irregularities, we have these tiny differences in the radiation field from when the very first photons started freely traveling through space. This is what that looks like. It's called the cosmic microwave background, which it literally is these first freely traveling photons. And you can see that it has these tiny irregularities where the red is, more energy and the dark blue is less energy. And those are from the quantum fluctuations, from the little energy blips that we were talking about. This radiation is everywhere, no matter where you look in space, absolutely everywhere. Doesn't matter. Okay, now putting a pin in that, going back to curvature. It is important. So we know the universe contains stuff because we are in it and we exist. Philosophers do not at me for that. Now, there's the set of equations that can tell us about how the universe is expanding. I'm not going to show you them because they're terrible, but they account for the quantity and what type of stuff is in the universe. But they also account for something called curvature, which we already talked about a little bit, and we're going to talk about now. There are three kinds of curvature. There's positive and negative and zero, which corresponds to universe geometry called closed, open, and flat. This was first examined experimentally by the WMAP satellite, which was a spacecraft that measured the little energy fluctuations in the cosmic microwave background that we were just talking about. And that's a remnant, like we said, from the early stage of the universe. According to theory, if the universe were flat, the angular distance between the brightest parts, so between like a red spot to a red spot, should be about 1 degree. Sure enough, the satellite found that the distance between the brightest parts was about 1 degree. Okay, so why does the size of the fluctuations mean anything? So if we keep talking about curvature and about how curvature bends light, the closed geometry, then the hot spots appear too large. Whereas if it's open, they appear too, but it's flat, the hot spots appear just right. And they appear just right. Amazing. Cool. I think that's so cool. Mathematical tangent. You'll notice here that there are triangles on all these diagrams. Do you remember in high school when you learned that the number of degrees in the angles of a triangle always adds up to 180? That was a lie. Just kidding, it wasn't totally a lie, but it was only part of the truth. That is only true for flat geometry. If you have a triangle on a positively curved surface, like a sphere, the angles add up to greater than 180, depending on how curved the surface is. And the angles add up to less than 180 for a negatively curved surface, depending on, again, how negatively curved it is. So anyway, The universe evolves, and therefore the way it ends is affected by the geometry of the universe. So each one of these geometries would cause a different fate. So given different quantities of things like dark energy, dark matter, and regular matter, and curvature, we can use these equations to predict the future evolution of our universe. Here we have a universe that decelerates and collapses back in on itself. Here's one that decelerates until it just stops expanding. One that expands at a constant rate, and one that expands at an accelerated rate, which is us. So let's start going through some scenarios. We'll start with the big crunch. The big crunch is, this GIF is a lot of artist interpretation, but it's at the very least accurate in that objects move closer and closer together. Galaxies merge, as the GIF shows. Eventually stars get close together. They start colliding. There's hot radiation everywhere. So you have like hot colliding stars sitting in hot radiation, and everything just gets super, super hot and nothing can hold itself together anymore. So you end up with a hot gas because everything just breaks apart. But also because stuff is coming together, stuff falls into black holes. So everything just gets sucked up by black holes in the end in this scenario, even though it, turns into a gas first, basically. But this is unlikely because the universe is flat. The big crunch is most likely with closed geometry. Also, dark energy causes accelerated expansion outward, not inward. In other words, it is accelerating, not decelerating. Okay, so dark energy makes the universe expand. That's why we can't do the big crunch, probably. Now, if the dark energy that's making the universe expand keeps leveling up and making it accelerate more and more, so the acceleration is accelerating, right? Then we get this thing called the big rip. Basically, the dark energy levels up and gravity can't hold stuff together anymore. And eventually neither can any other force. And stuff starts getting peeled away layer by layer, like big to small. So first, gravitationally bound galaxies are no longer gravitationally bound. Then the galaxies themselves start dissociating. The stars get yeeted all over the place, outward to inward. And then, if we're watching this from Earth, then our solar system gets yeeted out. The planets get yeeted out. Everybody's all over the place. Then, the layers of the Earth itself get sucked away, and eventually cells, molecules, atoms, and subatomic particles, everything just tears apart. And this ends in nothingness. Horrifying. But this is also not likely. This requires that the acceleration of the universe itself is increasing, but our acceleration is constant. So that's, maybe a mild consolation. But also this would require an open geometry, which is probably not the case. The third and last scenario I want to talk about is the heat death, or the big chill, or the big freeze. So these names seem totally unrelated, but they all refer to the same thing. Heat refers to maximum entropy. Entropy is a measure of disorder, and it's why you can't unbreak an egg, right? So in other words, heat death occurs when energy can no longer make anything happen. And to provide another example to hopefully clarify that, if you have a big pile of ice in a room temperature room, and then it melts, and then the water evaporates, the room ice system, it's no longer ice, but the ice that you had previously put in, anyway, it's now at maximum entropy because that system alone can't do anything different to the particles that used to be ice. Okay. So let's go through a timeline just for fun and terror. what might the end look like? About 10 to the 11, 10 to the 12 years from now, so super, super far into the future. Like, I don't think the human race even has to worry about this. All galaxies in the local group merge into one large galaxy. The local group is our Milky Way and the nearest objects. So they merge. Stars begin to die, and galaxies start fading because they are made of stars. Eventually, all the galaxies outside our local supercluster will recede, as they always have due to the expansion of the universe. So just quickly, the local supercluster is the cluster that contains our cluster that the Milky Way is in. So galaxies form clusters, and clusters form superclusters. And if you see local in front of something in astronomy, it just means it's our thing. It's like a Milky Way, a thing the Milky Way is a member of. Anyway, so the light from these galaxies becomes more redshifted as time proceeds until the wavelengths are too long to be detected and no information can transmit between any superclusters. Eventually, stars have exhausted their fuel. Low-mass stars have become white dwarfs, including our sun. Massive stars have exploded as supernovae, leaving behind neutron stars and black holes. And star formation, there's no new star formation. Stars are only running out. By now, planets have been ejected from their systems, or the orbits have decayed. Most objects are flung from their galaxies into space due to interactions with other nearby objects, and the rest are consumed by the galaxy's black hole. Then something kind of funny happens with protons. So currently, it's not known if protons decay or not. Part of the reason is that because if they decay super slowly. So a half-life is the amount of time it takes for half of a substance to decay into other smaller particles. So 10 to the 34 years from now, which is like an unimaginably long amount of time, half of the protons that currently exist will have decayed into other particles, like some photons, for example. And that's why it's so hard to experimentally verify. It's because the half-life is so long. But if this happens, half of all protons decay, then by 10 to the 40 years from now, all protons have decayed. The same applies to neutrons. The only particles that are left are photons and some other subatomic particles. There's still some black holes kicking around. But the black holes don't last for too long, because if Hawking radiation is real, black holes evaporate. Hawking radiation is a theoretical, it's the theory that black holes emit radiation at the event horizon, which is the edge of the black hole. So if they're emitting radiation, but they're not gaining any mass, then they're evaporating. So during this evaporation, photons and electrons and other particles that may have decayed already are emitted again. But inevitably, those decay as the previous ones did, leaving only stable particles. And by now, they're extremely unlikely to encounter and interact. So what is going to happen? Don't know. Absolutely nothing of what I told you in this talk was fact. It was all like maybe theory. We can't know. And we're probably not going to. Yeah. That's my talk. Please enjoy this meme about accelerated expansion. And I'll take questions.
Lauren, we have a question from the chat that says, science aside, which end of the universe do you prefer?
Oh man. I mean, I do like, hmm, that's a great question. I like the heat death because a bunch of stuff happens and then it's just like, I don't know, lonely particles flying around everywhere. And it's uniquely grim. I feel like it's just more grim than the Big Rip, you know? Anyway.
We have another question that is, what will live longer, the universe or the Queen of England?
Definitely the Queen of England. The particles are going to be streaming around at the end, like, and then the Queen of England is just going to still be there, just chilling with the particles whizzing around her. She's going to stay.
I actually have another question. So the gravity between like galaxies is gonna cause, the smaller galaxies to like kind of merge into the bigger galaxies and such. And then we have like the voids in which dark matter or dark energy is causing them to like expand. So is there like a cutoff between how many like galaxies merge together and those voids? Do you get what I'm saying?
You mean like, is there a point at which the dark energy would not push the galaxies apart?
Yeah.
No,
Okay.
I don't think so. Because, oh, well, no. So maybe actually. Because dark energy wouldn't push our singular galaxy apart because the acceleration is not accelerating itself. So there might be, but I don't know the specific answer to that question. Probably yes.
Right. So there's like
There's,
things that are going to
yeah,
start coming together and things that are going to start coming apart.
right,
So
right.
what that threshold is, like where the gravity isn't strong enough to merge and dark energy is taking over. You know what I'm saying?
Right. I'm not sure what the threshold is, but I mean the Milky Way is going to collide with Andromeda. Dark
Right.
energy can't stop that. They are destined to be together.
Oh, cute.
Cute,
Okay.
right? Anyway.
We have one more question. Since a lot of this is theory, is there some sense in which this is more like an art than a traditional science?
That's a good question. This is kind of like a very meta question, not in the Facebooky sense, in the original meaning of the word meta sense. Um, I think you could say that there is something artistic to theory because it does require a lot of creativity, right? It's just a different kind of creativity than, making a painting or something.
I think we still have time for a few more questions.
Yeah, we have one from the chat saying, why is the big crunch still even being considered if we know what we know about the expansion of the universe?
Oh, it's like not being considered. I told you about it because I wanted to illustrate how the different properties of the universe that we exist in would affect the endgame conditions. But people are like, this has basically been written off.
Okay, last question. If Hawking radiation exists, oh, sorry, you mentioned if Hawking radiation exists, how sure are people about Hawking radiation? Would it ever be able to be detected experimentally?
I'm not sure. It has not been detected experimentally. I think part of the problem is that too hard to detect experimentally because the radiation is so small. So it might not be possible. As far as the scientific consensus on whether or not it's real, I'm not sure. That's not my field. I kind of don't have an opinion on it, honestly. I don't care if Hawking radiation is real or not.
Yeah, as someone that studies supermassive black holes, I get that question asked, and I'm like, I don't know.
Yeah.
Okay, there's one more question, but I think we're gonna save it for the burning questions panel.
Thanks for the awesome questions.
Yeah, and we will see you back here in a few minutes for the panel.
Yeah.
All right. So next up with what's up for this month, we have Yaswan. And fun fact about Yaswan, he is an evil defector from our arch rival, the University of Texas, where he did his undergrad.
You know, I got to get the best of both worlds, all right? Hello, everyone. Welcome to What's Up, where every month I talk about what's up in the night sky. For those of you who are looking into getting to stargazing, here are some things you can look up to over the next month or so. Some fun things for you to look at, some tips as well. So this month we have some fun things for you. I guess the month's almost over, but first of all, let's talk about, getting up early in the morning isn't the best for everybody. There's some morning people out there, some people are night owls. I'm more of a night owl. But if you can get up early in the morning, there's some pretty great things to see over the next month. Mercury is going to be really, really nice to look at around this time of year. So if you go around February 8th, it's going to be at 13 degrees above the horizon. It's at its greatest elongation, aka the highest it's going to be over the horizon this month. And so if you're looking to go to Mercury, anytime around February 8th is going to be a great time to look at it. But again, you're going to have to go up early in the morning. You have to get up before sunrise because the sun's going to block out all of Mercury. But hey, fun fact about Mercury and Venus, because they're interior to the Earth relative to the sun, they actually have phases. So if you look at them over the course of a year or whatever, you'll actually notice that they have phases just like the moon. And so if you want to take a look at Mercury, which is traditionally pretty hard to see because its proximity to the sun, this is a great time for you to try to get that view. Venus is also going to be beautiful this month. It's going to hit its greatest brightness for the year around February 9th at around negative 4.6 magnitudes. Magnitudes, for those who are unaware, are this ridiculously stupid system that we use in astronomy to determine how bright things are. The lower the number, the brighter it is. And so, we traditionally say that the star Vega has a apparent magnitude of 0. Venus's apparent magnitude around February 9th is at negative 4.6, which means it's going to be roughly 100 times brighter than the star Vega. So that's pretty exciting. And then if you go February 12th, just a couple of days later, Venus and Mars will just be just about 6 degrees apart from each other. So that's about the size of, you stretch your hand out, that's about the size of, your 4 fingers of your outstretched palm, basically. So really, really close together. A great time for you to take a look at both of them. Also a tremendous photo opportunity for you astrophotographers out there. So, if you want to take advantage of this, you're going to have to wake up early, get up and get out there and take a look at some beautiful, beautiful planets. Next thing I want to talk about is when I talk about stargazing, one of my biggest recommendations is that you go to a pretty dark location. It doesn't matter if you spend a shit ton of money on a really nice telescope. If you're in the middle of the city, you're going to have a pretty bad view. The most important thing is you need to get to a pretty dark location. And I want to give you some recommendations for those of you who are in the Texas area, specifically those of you who are around the Bryan College Station area. Some places we can go to get some stargazing done, especially if you're someone who likes camping. So I'm going to give you some recommendations, and I put a star next to ones that I've personally been to. So those are the ones that I can personally recommend. And a couple of these are also stuff that my friends have gone to, and I trust their recommendations. And some of these are stuff that I found online and look like really, really good places. So near Bryan College Station, if you go just west of Austin, this is where I've done most of my camping so far. You've got Enchanted Rock State Natural Area, the Canyon of the Eagles Resort and Park. So Canyon of the Eagles is a private park, but it's actually pretty cost comparable to the state parks, which is pretty nice. Canyon of the Eagles also has a observatory on their site, so that's pretty nice. They have a bunch of nice telescopes out there. Pedernales Falls State Park is a really nice place. I've been there. It's a beautiful place. Inks Lake State Park is also a really, really beautiful place to go stargazing and to go camping around. And the picture here is one of the places at Inks Lake that I got from the Texas Parks and Wildlife's website. I've been to Canyon of the Eagles, Pedernales Falls, and Inks Lake. They're all fantastic places to go and visit. I have not been to Enchanted Rock, but I've heard beautiful things, and it is a protected dark area. So you're going to get really beautiful views out there. And these are all, pretty relatively close to Bryan College Station. So if you live in Austin, it's going to be even closer. But if you're in the Bryan College Station area, it's pretty close. It's not that far of a drive. Great places to go camping and go stargazing. A couple other places, if you want to go just south of DFW, there's Dinosaur Valley State Park, which actually has dinosaur tracks that are imprinted in the mud that you can go look at. I unfortunately was not able to go, but a whole bunch of my friends were able to go, and they absolutely loved it out there. And I've heard it's a pretty good place to go stargazing, and also, dinosaur tracks. How cool is that? Closer to the Houston area, we've got the Sam Houston National Park, Sam Houston National Forest, and the Davy Crockett National Forest, as well as the Brazos Bend State Park, which has an observatory on there that's hosted by the Houston Museum of Natural Sciences. So you can get a beautiful view out there as well from the Georgia Observatory. And the national forests, while they're relatively close to Houston, one of the nice things about forests is that the trees provide really great cover against skylight. So you actually get pretty decent stargazing out there. So there's just some opportunities to look at. Other great places to go in Texas if you're willing to drive a little bit further, or if you live in different areas of Texas. We've got the Big Bend National Park, which is the really big and famous one. We've got Big Bend Ranch State Park, which is close by. Over in West Texas, we also have the Devils River State Natural Area in West Texas, and the Davis Mountain State Park. Close to Davis Mountain State Park is the McDonald Observatory, which is an observatory that's owned by the University of Texas. But Texas A&M is a partner at McDonald Observatory. We've developed several instruments that we use out there, and they do public star parties and stargazing. They have a cool little museum out there as well. I've been there many, many times. This is actually a picture I've taken from McDonald Observatory. There's sort of two mountains out there, one mountain with a couple of telescopes and another mountain with the Hoppy Eberle telescope, which I'm showing in this picture here. It's a beautiful place, great place to go stargazing. I actually know a lot of people who retire out in that area, buy some land and build a house there, just so they can spend their retirement stargazing. It's a pretty nice place. If you want to go down to South Texas, we have the Resaca de Palma State Park, which has an observatory at the state park as well. So you don't even need to build a telescope or anything. They'll have a really nice telescope set up for you to look at a bunch of beautiful things. If you want to go up to the Panhandle, you've got the Copper Breaks State Park, and in the whole country, there's the South Llano River State Park. And all of these places are, so all the places here and all the places here are protected dark sites. And so you're pretty much legally guaranteed, for the most part, barring weather, of course, a pretty good view of the night sky. And so, if you want to get into stargazing, if you have a free weekend or whatever, I highly, highly suggest you go out to any of these places, check it out. You don't even need you don't even need a fancy telescope. You get some small binoculars, or, you can just get a picnic blanket, lay down on the ground, just stare up at the sky. It's quite beautiful. If you want to get to intro astrophotography, lots of phones these days come with astrophotography modes, which is something I never thought would happen, but here we are, and you can get all sorts of beautiful photos just from your phone these days. And so, it's just go up and get out and get camping. And that, my friends, is what's up.
What's up? So, funny anecdote. Just kidding. When does a story become an anecdote? I don't know. This morning I was up before sunrise or around that time, and I saw Venus, and it was so bright. For a second, thought it was an asteroid. I was like, "Are we gonna die?" But it was very early. I was not like awake yet, and so I was like, and then I was like, "Is it getting bigger? Is it? Don't look up." I don't know,
Yeah,
but
Venus is really bright. That's why they call it the morning star or the night star, because it's so bright and noticeable.
yeah. So definitely recommend people check it out. It's like extraordinarily bright. Um, so we don't have any questions. I do have one question. I don't know if you mentioned this. How far are the places in South Texas that you mentioned?
Right. So the one place in South Texas that I mentioned, let me share my screen again. So Resaca de Palma State Park in South Texas. So that's going to be over close to Brownsville. So quite far from Bryan College Station. Um, but if you happen to live near Brownsville, I actually have a lot of friends who live down that area, like McAllen or South Padre Island. It's not too far from that area. It's not so bad. Otherwise, if you have a free weekend, you're willing to drive, a couple hours, then it's also pretty worth going down there. But yeah, that one's down by Brownsville.
Thanks.
Yeah.
Any other questions? I don't think so.
Well, thanks for having me on again.
All right. Thank you, guys. Go look up in the sky this month. Go to some pretty places. All right. Up next, we have in the news with the one and only Dark Matter Dude. Lexi, fun fact about Lexi, he is a big Liverpool fan and gets into arguments with some of our faculty about it.
Yeah. Yep, that's definitely happened. Can't say much about it. Liverpool's great. The team I support. That's all I got. All right, yeah. So I'm gonna talk a little bit about what happened in the news. So let's share that. And here we go. So nope, not letting me do that. Okay, cool. Yeah. So the big story, the thing that's sort of dominated all the headlines is that JWST is like a proper space telescope now. It was launched December 25th. It was an excellent, Christmas morning present for all of the at least like American hemisphere astronomers. It had like it was a smashing success. There was enough fuel. So JWST launched with enough fuel to nominally go for 5 years. That was the guaranteed amount of time that the telescope would be operational in space. Because the launch was so successful at every single point on getting its way out to where it was supposed to be, it has enough fuel reserves to last significantly more than 10 years, which was like the at least sort of best case scenario that people were drawing. So the fact that we're going past that is just amazing. We're going to get so much science out of this, and everyone is really, really excited about it. The sun shield deployed. So I have a little GIF here of JWST being folded up. That's because it's such a large telescope. We have to fold it up in order for it to fit inside of the rocket and get launched up into space. And so there's this really complicated procedure where it kind of unfolds, the mirrors open up, and the thing at the bottom is called the sun shield, which is what protects the telescope from infrared radiation just from Earth and the sun, because it turns out that those things are hot and emit at wavelengths that would just wash out anything that JWST is trying to look at, the very faintest galaxies as far as the wave. So the sunshield deployed was worked wonderfully. Right now on the hot side, the temperature is around 130 degrees Fahrenheit, and on the cold side, it's minus 350 degrees Fahrenheit. So incredibly hot on one side, incredibly cold on the other. That is most of the way to kind of the final stage of how hot and how cold that's going to be. But there's we're still in the process of cooling down the cold side of the telescope. It'll get a little bit colder before we say, okay, now we're good. We can turn on all the instruments and start turning on lots of the telescope. Currently, so JWST is going to live outside L2, which is sort of past. If you can imagine the Earth going around the sun, and then the moon going around the Earth. L2 is kind of a gravitationally stable point that's outside of the Earth-Moon orbit that kind of moves with the Earth around the sun. So there's other telescopes that have been put out there. Right now, it's orbiting with Gaia, which is objectively the best telescope, a European space mission that I use a lot of data for. But yeah, so the telescope is currently going through its kind of commissioning phase, and then after that, it'll start doing sort of the first science targets that it was supposed to point at. And then it's game time. We're just gonna use this telescope. We're gonna get as much science as we can out of it over these significantly greater than 10 years that it's gonna be available for. All right, now one piece of science news that's near and dear to my heart because it's also Milky Way science. Is sort of an unraveling of an ancient star cluster. So in astronomy, we use the chemistry of stars to kind of learn how far along in the universe they formed. So we call that chemistry. We kind of an easy version of that chemistry is the metallicity, or how much iron relative to how much hydrogen is in a particular star or cluster of stars, and that's more or less a tracker of age. So as there are successive generations of star formation happening, the earliest stuff, there's only hydrogen, helium, a little bit of lithium, and so those are very pure stars. There isn't any iron at all. And then as time goes on, you get more and more of these heavier elements, and your younger generations of stars are much more of what's called metal rich. And so metallicity is a tracker of age, basically. So star clusters, the ones that have been observed in the Milky Way and other nearby galaxies, all have this sort of metallicity floor. You don't really see star clusters that are below a certain metallicity. And so for a long time, people have been trying to figure out, okay, were there earlier generations of star clusters that have these lower metallicities that for some reason, we can't detect them anymore for whatever reason, or is there something physical happening where there's just a floor that we don't get clusters that are older than that. And so this new study, this team of scientists went out and got metallicity observations for what's a stellar stream around the Milky Way. And so what this stream is a globular cluster that came in to the Milky Way, and because of the tidal forces of the Milky Way, ended up getting ripped apart or unraveled. And when that happens, you sort of stream stars across the sky, and that's what's called the stellar stream. And so these stellar streams are the remnants of currently being eaten star clusters and galaxies. And so the cool thing about this stream that a lot of press has been going out for is that this stream is actually has a metallicity that's below that of this metallicity floor. And so it's 0.04% the metallicity of the sun, which is incredibly metal poor, very old stellar populations. And this is a unique window into galaxy star formation and galaxy formation. Now that we have found something that is as old as the star cluster, now that we know these things can exist, they just maybe get sort of ripped apart before we can observe them at the present day, at this current time in the universe. And so this tells us a lot about how the earliest stars and earliest galaxies formed, which is one of the goals of astronomy. It's like, how did we get here? And so I always like to end on just a really cool image and not go too deeply into the science here. And so this paper, sort of series of papers, came out in a big press release today, and the images are just stunning. So these maps are it's a map of the radio emission at the very center of our galaxy, the centermost, like 6 degrees. So not that much distance spread across the sky here. But this radio emission of the galactic center, the center of our galaxy, we can see these really awesome features, like all these solar globs are stars either forming, being born, or dying off in big explosions. We can see at the very center here, that's the supermassive black hole that's at the center of our galaxy. That's sort of just shredding off a whole bunch of radio emission, and it's super bright with these telescopes. And these strange filaments here, we actually don't know what these are. We've known about these things, that they're highly magnetized, very radio loud lines, and we've known about them for like 35 years, but no one has any idea what they are or how they form. And that's actually kind of one of the key projects from this radio survey telescope that these results are coming from. But yeah, this is just like the coolest image, and I've been staring at this all day, and it's fantastic. But yeah, so that was what was in the news the past month.
Wonderful. Thank you, Lexi. I do agree with the comment in the chat. Definitely a good new desktop background.
It looks like we don't have any questions. But yeah, no, all of that always really interesting. Thanks. Dark matter, dude. What is dark matter? So I think next we're gonna invite all of the peeps, all of our astronomers back. Peep, Cosmic Kid, Lauren, DMD, just kidding, dark matter dude. Okay, and this, I'm sorry. This is our panel for today, presenting the Burning Questions panel, and I'm going to be the host because I know all the questions. So are you guys ready? How are you feeling today?
Ready.
So ready.
I'm a couple whiskeys in, so pretty ready.
Oh, the questions are really good. There's a few that Lauren already answered, like what the hell is dark energy? And what is dark matter? So we're not going to get into it. If we have some time and y'all want to explain, sure. But let's do one that I think was relevant. So you guys talk about elements a lot, but what does astronomy have to do with chemistry?
So all the elements came from space, right? So all heavy elements are from supernovae, for one.
Okay.
Yeah, chemistry actually has a lot to do with space. So we can learn a lot based on where different elements come from different physical processes, astrophysical processes in space. Supernovas are one way to create elements. Star fusion is one way to create elements. We get a lot of different ways to create a lot of different elements. And so we can use these to trace lots of very useful processes. For instance, in galaxy formation or quenching, there's lots of different elements that are very useful for tracking how different processes are working. Nico probably knows more about this than I do. Nico, aren't you passionate about some of these lines going on?
So I'm very passionate about certain things, but everything that I study is more or less all hydrogen or other very light elements, helium, neon, and such. But in essence, sort of a broader answer to this question is astronomy is nothing more than chemistry in the sky. And everything that we do realistically, other than I don't know, I guess other than like neutrinos and gravitational waves, like everything else stems from chemistry.
Nico, can you briefly explain my passion joke for those who don't know?
Sure. So passion, I'll throw it in the chat. So the passion series is a set of transitions of the hydrogen atom. And so my research for the last 3 years has been studying the passion series. So it has become a running joke that I'm very passionate about galaxies and about star formation.
What do the passion lines tell us?
The passion lines tell us all about how stars form in other galaxies. I'm particularly interested in galaxies that are very far away from us. And basically, in short, the passion transitions of hydrogen are the best, and you cannot convince me otherwise. The passion lines tell us all about these big, violent, hot stars as they're forming in galaxies way far away. And I'm not going to say that they're perfect, but I'm going to say that they're certainly better than more traditional means of detecting stars and star formation in other galaxies. But yes, it all comes down to chemical transitions of the hydrogen atom. So more or less everything we do is chemistry.
Yeah, great. So it's all related chemistry, math, because you can also argue that everything has some mathematical formula to explain it, and then there's physics. But okay, next question. What's the deal with a new moon in a moon cycle?
What's physically creating the new moon, or like more metaphorically, what's the deal with the new moon?
I think this question is right. It's kind of asking like, why new moon? What is it?
Right. So
Why a new moon?
physically what's happening is as the moon orbits the Earth, because the orientation of the sun, the Earth, and the moon, which is orbiting around the Earth, the moon doesn't inherently give off any light on its own, at least not light that we can detect with our eyes. No visible light is being created from the moon. And all the light we see from the moon is just reflected sunlight that's being reflected off the surface of the moon. But because the moon is rotating around the Earth, the sunlit side isn't always going to be facing the Earth. And so when the moon is roughly between the Earth and the sun, the sunlit side of the moon is going to be facing away from the Earth. The darker side of the moon is going to be facing the Earth, which is basically what's causing the new moon. And then the opposite is for the full moon. That's when the sunlit side is completely facing the Earth. And so we see a full moon. That's why we see all the different phases, because in between, only a certain percentage of the sunlit side will be facing the Earth. So we'll see only a portion of the moon. So that's where we get all the phases from. At least that's what's physically happening. More metaphorically, what's the deal with the new moon? I don't know. Whatever it means to you is what's the deal with it, I guess.
Thanks. Yeah, it's just a cycle. Just a plain old cycle. Okay. Does the sun move? This is like a heavy question.
Yes. No, I'm ready for this. All right, yeah. So does the sun move? The answer is yes, and it moves on actually a lot of levels. So one thing that I kind of love about that kind of blew my mind once I thought about it was that for the same reason that like you are attracted to the Earth via gravity, the Earth is also attracted to you. Same thing. And so that kind of reciprocity of gravity extends to all of the other planets and their attraction to the sun. And so as like Jupiter and Saturn and all these other larger planets are going around the sun is also orbiting around, their common center of gravity, basically. And so the sun like wiggles around, and sometimes that center of gravity is actually outside of the sun, which is utterly ridiculous to me. So that's one way. The second way is actually, so the sun is located in a galaxy called the Milky Way, and it's our home, our like cosmic home. And the Milky Way is a disk galaxy, and it's sort of rotating in this plane, kind of around the center. And so, because of that, the sun actually is going around, orbiting around sort of the center of our galaxy. And another really awesome fact is just based on how far away the sun is, and sort of how things line up. When the Earth was populated with dinosaurs, the sun was actually on the opposite side of our galaxy, and so that kind of traces this larger history is connected to where the sun was in relation to the galaxy, which I think is super cool.
Turbulence. Lots of turbulence. Okay, so I'm going to ask one from the chat that was asked earlier. So this goes back to the 3 different scenarios of how the universe will end. Dun, dun, dun. So what kind of sci-fi solution exists to prevent any of these scenarios?
Oh my God. Do I know of any sci-fi media off the top of my head that deals with stopping the end of the universe? No. So
get
I
a
guess,
new universe.
Right, get a new universe. Open a portal to Despondos.
I mean, it's so far away. It's like stop time.
Right, it's like
figure out how to stop time.
Like we would have to figure out either that or stop dark energy.
Ooh, it'll be the fight of time versus dark energy.
Make a dark matter generator that prevents dark energy from expanding everything.
Right, because if you have this theoretical dark matter generator and you spit out so much dark matter, which is massive, then maybe you can spit out enough dark matter that the gravity is stronger than the dark energy.
I'm gonna yes and that, and we'll say that we still conserve energy and mass, but we convert the dark energy into dark matter,
I like it.
So we're not even breaking the laws of physics. Too bad.
Only a little bit of law breaking as a treat.
I love it. This should be the next sci-fi movie. Okay, next question. Why does JWST orbit around L2? Why doesn't it just try to sit as central as possible?
So the more or less the shorter answer to that is just because it's easier. Because in theory, if you have a perfect system of masses, then your L2 Lagrange point is just one tiny little point in space, one infinitesimal spot. So more or less, it's just practically impossible. So one thing that we do know really well, as we've been doing for the last 70 years, is throwing things into an orbit around something. So that's something that we can do. And it's something that we can calculate very well where it's going to be at what time. So more or less the answer is it doesn't need to be sitting in one specific spot. So we know how to control its orbit. So we'll control its orbit in a relatively tight circle around the L2 point.
Right. And that's also why recently the launch and the corrections were very important, because to keep it in orbit, you have to make little corrections to the orbit every now and then, which costs fuel, which is a really big deal when they're launching it and sort of make sure it's on the right path, that they were able to conserve the fuel really well and essentially double the lifespan of JWST, because they're really, really good at making course corrections. And so because it's not just stationary, because it's orbiting and has to make those course corrections, that does limit the lifespan of JWST. So it's some really, really good engineers out there who were able to conserve enough fuel to essentially double the lifespan and get as much science out of it as possible. So that's going to be really awesome.
Supermassive black holes. They're going to be able to, with the resolution of JWST, we're going to get some really great measurements of supermassive black holes and also other science that is very important. So, okay, next question. Does the pub have any opinion on any of these astronomy questions? Very important. The important question of the night.
No, the pup has no opinions on astronomy questions. The pup just wanted attention. She was whining at me until I picked her up and pet her, and then immediately ran away because she didn't want to be picked up. So who knows what's going on in her head. She's currently in my bedroom, probably asleep on my bed right now, and I'm going to have to kick her off when I go to bed, probably. We'll see.
For what it's worth, my cat just looks vaguely annoyed that we're not cuddling on the couch.
Ah, typical annoyance. Classic. Okay. What's your favorite part of Starlink? Yay.
Triggered.
Ellie, I see you. None. No part of it. Literally zero.
Do we want to explain why we don't like Starlink?
Yeah. I guess I'll do this because I a couple months ago or maybe over a year ago, man, I gave a talk on why I don't like Starlink. So the basics is that Elon Musk's satellite internet company is launching a whole bunch of these basically tiny satellite relay things that are in space. And so the idea is to constantly have a whole bunch of almost like little CubeSats flying around space, and you can get pretty consistent internet coverage wherever you are on the globe. That's the gist. The problem is that these things are basically disco balls in space. And so they reflect a whole ton of the sun's light back at us. And so they're actually bright enough that if one is flying by, you can especially, it's easiest to do this when it's either the sun is setting and you're about to enter twilight, or the sun is rising, and whatever that is. And you can just see like streaks of lights going in a particular direction, all following the same path. And so that's bright enough for like us to see as humans. And if you point a really sensitive, really large telescope in the same direction, you'll just see these massive streaks of light across your image. And so like you can do things to sort of subtract out that signal. But then you're missing the part of the image that's below it. You're not going to be able to get that back. And so if you're doing something like trying to take a whole bunch of pictures of the night sky over the course of several nights and have these really sensitive maps, the amount of times that you need to return to one patch of sky just increased because some billionaire put a whole bunch of disco balls in space. So that is that's the gist of Starlink, and part of a large chunk of why astronomers in particular don't like it.
That's the favorite part, huh? Okay, so next question, do galaxies die? This is actually a question I got asked by third graders.
So the question is, do galaxies die? This is rather multifaceted on what you mean by die. But in extragalactic astronomy, we usually refer to die as the technical term being quench. And when we say quench, we mean no longer forming stars. And the answer is definitely yes. Galaxies, as they go throughout their life, they will go through periods of star formation, either long continuous star formation over their entire life, and they'll kind of fizzle out slowly, or some galaxies will create enormous amounts of stars very quickly and then shut off completely. And so when the epoch of star formation ends, we call that galaxy now quenched. And quenched, you can colloquially interpret as dead. So yes, galaxies definitely do die.
Okay, I see what you're saying. But as an extragalactic near redshift astronomer, I would say that they're not necessarily dead. I mean, the galaxies are still there and we're still studying. Yeah, by that definition, I guess they would die, but my galaxies are still important, even though they're not forming stars, you know?
Listen, just because you're dead doesn't mean you're forgotten until you are forgotten.
But are you observed? Being observed. Okay. We'll talk later. So next question, can you detect a soul? It's a little pseudoscience-y, but
That feels more philosophical than astronomical.
I can say for certain that astronomers have not.
I don't know if that's an astronomy question. I think that's just like a being a person question. Maybe.
okay, so short answer, no. I don't know. Who knows? Okay, next question. Do any of you have thoughts on astrobiology, in particular trying to start life on another planet, whether it would ever be possible? So thoughts on astrobiology, starting life on another planet. Could it be possible?
So I'm very pro studying other planets to try and detect life. I think part of what kind of gets mixed up in astrobiology study and why a lot of people are really interested in it is to use this idea of like something like terraforming another planet to escape very existential threats that we're experiencing on our planet. And that's not how this works. You know, it's way easier to save the planet that we're on that we know supports life than to try to make some other planet like hospitable to at least humans. And so I decouple those two things in my brain. So I think like studying other planets to try and find signs of life, either current or in the past, is very useful. And then in terms of using that as a bridge to the future of humanity, like maybe very, very, very far into the future, but there's other problems that need to get solved before that.
I'd like to add that in addition to, you know, it's just way harder to terraform Mars, for example, than it is to just do responsible things on Earth, of course. Are we going to be able to pick up ourselves and go to a planet that already could support life? Like, personally, I don't think so, because everything is so far away. So far away. It's just not realistic.
Everything is very far away, you're right. Okay, next question, the one that we might have answered in a previous talk, but I think people tend to question a lot. Why do black holes suck up stuff?
Sylvie, you're the black hole expert.
What? I mean, I can explain, yeah. Sure, why not? So the reason why black holes suck up things or pull things is because of their huge gravitational attraction that they have. So they're like the largest, most dense objects in the universe. And they're so dense, so compact, and pull things that the fastest thing in the universe can't actually escape. And the fastest thing is light. So the reason why black holes suck up everything is just because they're very massive and very dense. Just like the Earth. I guess you wouldn't say the Earth sucks us, but the Earth pulls us down or we fall into it. That's how strong the gravitational influence of the black hole is that it doesn't let anything escape. Anyone else want to add to it?
Oh, you did perfectly.
Black holes. Okay, last question. I don't think I see any more in the chat. Last question. Okay, this is a little funny one, but what if the core of the sun was a piece of a core-sized onion?
Oh, okay. I have to assume that this is either Curtis or Addie in the chat. Yeah, so if the core of the sun was a core-sized onion, I believe we determined that not much would really change. I suppose if you
Well, wait.
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 Go ahead, Lexi.
I want to push on that for a second. Are we talking about an onion, like of normal onion density, but the size of a core?
Yeah,
Yes.
so that was the original postulate of this question.
Because then it's not dense enough. You can't fuse.
Right. And like
so,
onions don't do fusion.
right, I think it would collapse.
You wouldn't have.
Well, sure, but it would collapse and then fuse. Like there's plenty of mass in a
Counterpoint.
sized onion.
Counterpoint, if it was the same density as an onion but the size of the core, it would not collapse because the reduction mass would be so large that the convective energy of the outer layers would basically just blow it apart because there wouldn't be enough gravity to hold it in.
I appreciate the spirit of this question, though. It's like,
I do.
Like onions have layers and stars have layers. So, yeah, I think we would just have like an onion in space.
Well, so the sort of back of the envelope density number for the sun is that it's approximately the same as the density of water, like within a factor of 2.
Oh.
So
which is about the same as an
the
onion.
density of an onion is approximately the density of the sun.
Well,
So
I'm wrong then. Never mind.
I would go back to my original statement and say not much would change.
Oh.
What about the radiation?
Well, you'd still have issues with. You'd still have issues with if the core is an onion, you wouldn't get fusion anymore.
Right.
Right. That's. Continue.
Yeah.
Sorry.
No, I mean you couldn't get fusion anymore because how would fuel get to the center to fuse? The onion's not going to fuse.
Is the onion moving?
I'm still on my theory that it would blow apart into a molecular cloud, and then over the course of millions, if not billions.
Yeah, actually, another really important thing is that the core of the sun is much denser than the sun on average.
Right.
Sure.
And so, yeah, so fusion wouldn't happen. I think there'd be a couple cycles of convection, and then that would stop because you're not heating the bottom part anymore, basically.
So we would just have an onion in space, like a big ass onion.
Or would like the stuff, or would the onion burn first, and then
the onion would burn first.
Okay,
it would
yeah.
burn through.
Well, okay, no, wait. I think that depends on if it started as an onion or if we just take out the core and we like magic in an onion. Because if we take out the core and magic in an onion right now, it's gonna burn. But if it was always an onion, like
I thought we're just magicking in an onion.
We need more bounds on this question.
So I propose that somebody designs a simulation of a stellar interior and replace it with an onion, and then tell me the answer.
That's a good project.
Well, I mean, in essence, you're just increasing the metallicity of the sun, of this core of the sun, right?
I think we should bring these up to the professors and make grad students solve this problem.
No, it sounds like Nico. It sounds like an order of magnitude problem for you to solve.
Or an order of magnitude problem. This is gonna be the last question. You guys can answer it fast. How long till? Well, no, not that one. Will Venus and Mars being 6 degrees apart in the sky have an effect on my daily astrology reading?
Only if you let it.
Oh. Good answer. Okay. All right. Lightning round. Name your favorite object in the universe. Nico.
Goods North 34456. No one knows what that is, but it's fine. It's a very pretty galaxy. Go look it up.
I'm gonna look up. Okay.
Sylvie froze.
Yeah, we might be losing Sylvie. We can go around everyone else's answer. My answer was gonna be my cat.
Aw. Mine was gonna be Supernova 2014J, but I started rethinking that when you said your cat.
My answer was going to be you.
Aww.
Well, now I just feel shallow.
Me too, Nico.
Oh, Sylvie's
bye,
gone.
Sylvie.
Absolutely.
Nico's the
like,
host
like,
now.
like actually got Nico's in charge. I guess Nico is an MC. You can end this if you want.
Yeah, Nico, what's your
Nico's-
burning questions for us?
Nico's the captain.
I am the captain. Okay. Well, in that case, we shall go on to the trivia answers.
Woo.
Assuming that Silvana doesn't come back. She's texting me now, frantically trying to get back in. Okay. One moment, please.
And we're back.
Oh, okay.
Did
Timing.
anything happen while I was gone?
No, we answered the last question and we are about to go on to trivia.
All right, trivia answers. Can you see the trivia answers? Okay. There they are. Okay. Trivia answers. I'll start. So question 1, how big are the primary mirrors of JWST and HST? The answer is JWST is 21 feet and HST is 8 feet.
All right, our second question, what wavelengths can the James Webb Space Telescope see? 100 nanometers to 2.5 microns, 0.3 millimeters to 3.6 millimeters, 0.6 microns to 28 microns, or 55 microns to 672 microns. The correct answer was C, 0.6 microns to 28 microns.
Oh, the first one is Hubble's wavelength range. Question 3, how big is the JWST sun shield? It is half of a tennis court.
Question 4, which telescope was launched into space by a shuttle? Hubble, James Webb, neither or both? The correct answer is the Hubble Space Telescope.
JWST was launched by the Ariane 5 rocket. I actually don't know. Question 5, how far away will JWST be? The answer is C, 1 million miles. Hubble orbits at 350 miles, and this is their respective distances. Not to scale, maybe to scale.
Not to scale.
Not to scale.
Question 6, when was the original launch date for JWST? If you were here in December, you would know that it was 2007. It's been a long time.
Question 7, what is the name of the first telescope to orbit L2? Herschel.
Question number 8, how many instruments did each telescope, was each telescope originally designed to hold? The correct answer is JWST is slated to hold 4 instruments, while HST designed to hold 6.
Question 9, what was the original name of JWST when it was proposed in 1996? And the answer is, it was the Next Generation Space Telescope, NGST. NGST became the James Webb Space Telescope in September 2002.
And last, who is Hubble? The correct answer is B, Edwin Hubble, who discovered that there are other galaxies other than the Milky Way.
Like the Hubble constant. And that is trivia. And that is our Astronomy on Tap. Just quick reminders is that our next one is going to be February 23rd at the Grand Stafford Theater and also on YouTube, hopefully with less technical difficulties.
Make sure to go and subscribe and like all of our social media. Go ahead, you're all on YouTube right now. Go ahead, hit that red subscribe button. Follow us on Instagram. And remember, we have these beautiful shirts and these brand new mugs. $15 gets you a free one. We are available on Venmo and Cash App. And when we are back in person, we can take cash donations next month.
Cash donations too, yeah. And we have cool swag. Okay.